this solution fails for the memory operations. We just talked about this. So let me go to the next. Unfortunately, that bypass and forward solution sometimes won't work for the memory operations. Like if you take the instruction 1, 2, 3 here, the first instruction is a memory instruction that reads the value from the memory where R2 holds the address of the operand and reads that value and write it into a register or move that value into a register R3. Whereas instruction 2 that adds R3 and R5 and moves the result or write the result back into R4, whereas instruction 3 adds R7 and R8 value and writes the result back into R6. So in the pipeline execution, if these instructions are executed in this sequence, suppose, okay, so then instruction 1, move instructions enters into the pipe in the first stage. In the second cycle, it will be decoded. So in the decode stage, it finds the R2 which holds the value. That is the register addressing mode, register indirect addressing mode. So it finds the base value, base address plus the R2 value. So that will be decoded. Instruction 2 enters into the pipe in the instruction fetching stage. At the third stage, the instructions enters into the execution stage. So the ALU that computes the address of the value, which is known as the effective address of the data memory. So if instruction 2 enters into the instruction decode stage, so instruction 2 will not get the correct value from R3. Why? Because the result is not yet loaded into R3 by instruction 1 at stage 3. Okay. So at the fourth instruction 3 enters into the pipe at instruction fetching stage. So at the fourth cycle only the data will be read from the R3 memory, and that can be forwarded back to the register 2. But that's at the end of the fourth stage. But instruction 2 needs the R3 value during the third stage. So this bypass and forward solution fails in these kind of conditions. So if it enters into execution stage, it reads a wrong value from R3 and instruction 3 enters into the instruction decode stage in the pipeline. Okay. If this hazard is not there, then these 3 instructions completes their execution in 7 cycles. If this load use hazard is not there, then what is the solution? The solution is instruction 2 must be stalled to get the right value. So what is there? At the third stage, instruction 2 enters into the instruction decode stage. At the fourth stage, the data will be read from the memory that is not yet updated in R3. So instruction 2 stops its execution in the pipeline. Then all the following instructions also stops their execution, like instruction 3. Then at the fifth stage, the instruction 1 completes its execution. in the first half, and instruction 2 will get the value from the interstage buffer after fourth stage, which is not yet updated in R3, but the value can be forwarded from interstage buffer. So that enters into execution stage. Then the instruction 3 enters into the decode stage, and they continue their execution smoothly. So they complete their execution in 8 cycles. So what is the cycles per instruction here means 8 cycles. Okay, the cycles per instruction is equal to 8 over 3. So that gives some kind of 2.66, something like that. Okay. Yeah. So in this case, what will be the solution then? So the solution for this kind of instructions is to rearrange the instructions. That we call instruction scheduling. So that is instruction scheduling means instruction 2 is depending upon instruction 1, but instruction 3 is not depending. So if there is a good compiler, the compiler can reschedule these instructions for execution, that is out of order execution. That is, first allow the instruction 1 into the pipeline, then the independent instruction, then the dependent instruction. So now see the difference here in the execution by reordering. Instruction 1 enters into the pipeline in the first cycle. At the second cycle, 2 instructions will be there in the pipe. Instruction 1, that is in the instruction decode stage, and instruction 3 allowed inside the pipe, not 2. There is no dependency here. So at the third cycle, instruction 2 executes the instruction 1, which computes the memory effective address. And then instruction 3 moved into the next stage in the pipeline, instruction decode, and instruction 2 enters into the pipeline at instruction fetching stage. Correct? So at the fourth cycle, the R2 value, the register indirect memory access, the value is read from the data memory, and that is ready in the interstage buffer at the end of fourth stage. And instruction 3 enters into execution stage. Instruction 2 decoding. So the source 1 operand is reading from R3, source 2 that read from R5 register. So at the fifth cycle, in the first half, right back stage, this value, the operand from this location that will be updated in R3 register, the load operation. Then instruction 3 enters into memory access stage. Instruction 2 gets this value which is present in the interstage buffer for execution by the ALU. So then the instruction 3 completes its execution in fifth cycle. Instruction 2 moves into the memory access stage, and instruction 3 completes its execution in 7 cycles. So this is the advantage of instruction scheduling. So this depends upon a good compiler. So this is the second solution for the read after write operation. The read after write operation.